Okay, welcome to this video go through of the Edexcel International GCSE for Physics. This is the summer 2024 paper. This is paper 1. Okay, so question 1, we're asked to show a diagram of the moon orbiting the Earth. I would draw the Earth as a point like this, and the moon orbits in a circle around the Earth, something like this. Okay, there's one mark for drawing it as a circle, one mark for drawing the Earth at the centre of the circle. The force is the gravitational force. Okay, don't use the word gravity. Gravity is generally just a bad word. The gravitational force. Give the name of another object that orbits the Earth. It would be a satellite, an artificial satellite. I think I'm thinking of some sort of satellite, the space station, something like that, but some sort of artificial satellite. Final question then, planets and a comet orbit a star. What's the difference between the orbit of a planet and a comet? They want us to write this. A comet, comets orbit in elliptical paths. Okay, they sometimes ask us to sketch this, don't they? If our star was like that, a comet would be an ellipse around it, something like that. Star, comet. Okay, 5 marks for that question. Okay, question 2 about radioactivity. We have carbon. Carbon has 6 protons. Okay, a different isotope that has the same number of protons, so it's going to have 6 protons. This is the same, exactly the same isotope, because it's got 8 protons, so it's not that one, so it must be this one. The answer is A. What type of radiation is a high energy electron? Okay, an alpha particle is a helium nucleus, a 4-2 helium nucleus. A gamma ray is a pulse of electromagnetic radiation. Beta particle is an electron. C, a nucleus emits radiation. This causes the mass number to decrease by 1. The atomic number stays the same. What type of radiation is this? This is actually a neutron emission. This is quite a sort of a question that people are likely to get wrong. So we have, for example, say that carbon 14. We have something like this, and we go down to the mass number decreases by 1, so it goes down to 13. So it stays as carbon, and the question is, well, what's released? The missing thing is got a mass number of 1 but no atomic number, which is a neutron. So yeah, sometimes isotopes can shoot out a neutron. That's what's going on there. Nucleus of uranium is this. How many electrons could be in it? Well, we're told it's positively charged. Okay, if it was an atom, it would have 92, but it's not. It's positively charged, so it must have fewer electrons than it has protons. It's got 92 protons, so it's going to have less than 92 electrons. Radioactive isotope has this activity. The half-life is 8 hours. What's the activity after 16 hours? Well, I draw them like this. In 8 hours, it's going to go down to 200 becquerels. In another 8 hours, it's going to go down to 100 becquerels. The answer is 100 becquerels. Question 3. Okay, this time we're being asked about infrared radiation. What's the harmful effect of it? Infrared is going to burn the surface. So I would say something like damage to the sort of skin, burns, but I think specifically the key word you're going to want to talk about here is the sort of surface. You're burning the surface of your skin, something like that. Heating lamps produce visible light. What are 2 similar properties of visible light? Well, they're both electromagnetic waves, would be my first one. Both electromagnetic waves. They're both on the electromagnetic spectrum. They both travel at the speed of light, 3 times 10 to the 8 meters per second, in a vacuum. Something like this. Okay, and then the next question is, what are the differences? Okay, so infrared has a longer wavelength. Okay, the electromagnetic spectrum is all about different waves that all have different wavelengths and different frequencies. So infrared has a longer wavelength, and visible light has a higher frequency. Now, clock my language here. When I'm talking about wavelength, I'm talking about long or short. When I'm talking about frequency, I'm talking about high or low. Okay, we're still going with this. Infrared lamps placed 1.5 meters. How long does it take for the waves to reach the car? This is we're doing time is equal to distance divided by speed. The distance it's got to cover is 1.5 meters. The speed is 3 times 10 to the 8. When you put that into your calculator, you get 5 times 10 to the minus 9 seconds. Okay, I should say it's probably a 2 significant figure number, isn't it? We've got 2 significant figures here, 2 significant figures here, so I should probably leave my answer to 2 significant figures. Okay, paint takes less time to harden when it absorbs more energy. We observe that white paint takes more time to harden than black paint. Okay, so this is going to be to do with black being a better absorber. It's all about absorbing energy here. So black is a better absorber, it's a better emitter as well, but we're talking about absorption here. Black is a better absorber than white. Okay, so what does this mean? It means black absorbs more energy in the same amount of time. Okay, if we've got the same amount of time, however long it is for this this car to dry, black's absorbing more energy. Okay, evolution of a star, main sequence star, is created in a collapsing region of nebula, different energy stores that's happening. So the key thing is, you know, that we're talking about a nebula starting to collapse just before the main sequence star. Quite a hard question, this one, actually, I think. They have to just expect you to know what's going on, but here, sorry, know what the definitions are, whereas here they actually expect you to understand what's going on. Right, it's the chemical store of energy. We've not got really any chemical reactions happening here, so that's not something particularly relevant. Now the nebula starts to collapse. Gravitational potential energy is essentially a measure, you know, we'll be thinking of it as a sort of a measure of how high up something is, tells us the gravitational potential energy. But if we've got, you know, a big star, you've got objects out here on the outside which have got a lot of gravitational potential energy. As that compresses to a small star, we've got less gravitational potential energy. Okay, so that's gone down. Nuclear, because I think it's before the main sequence star, we're not doing any nuclear reactions. The whole point of a nebula is we haven't started the fusion process yet, so we're not doing any nuclear reactions, no nuclear energy happening here. And then thermal, we know from gas laws, as something reduces in size, it increases in temperature. So as it gets smaller, it gets a lot hotter, and presumably hot enough to start some fusion. At the end of the main sequence star, the star becomes a red giant. Give the property of a star which determines whether it becomes a red giant or a red supergiant. Red supergiants are the biggest stars turn into red supergiants, so you know, how massive it is will affect that. Okay, giant star, a red giant eventually becomes a white dwarf. what are the differences? Okay, so a few things to say here. A red giant is larger than a white dwarf. Okay, the clue's in the name, but it's still worth saying. Red giant, much larger. Okay, it's also red. What does that mean? A red giant is much cooler. Okay, because it's increased in size, it's cooled down. That's what the red means. Okay, then there's a few more things you could say. A red giant fusion is still happening. A red giant still has fusion taking place. Okay, it's still doing those nuclear reactions, whereas a white dwarf is not. A white dwarf is essentially a dead star. And then, I'm not sure what could we say as the final thing, something about density maybe. A white dwarf is denser than a red giant, something like that, because it's just a very dense core left over, something like that. A few different things you could say there. I think those are the first 4 things that came to my mind. Okay, Hooke's law. A graph. You can label these equations either way around. I prefer to have it as force on this axis and extension on this axis. Now, extension is going to be measured in meters, force is going to be measured in newtons. It's directly proportional. What does that mean? It means it's a straight line going through the origin. Do that with a ruler in your exam. Should label both axes with physical quantities. Lovely. I think we've got that there. What do we have here? We have an object on a spring. Okay, we pull it down and release it. Determine the magnitude of the resultant force. Well, it's got 2 newtons going down. It's got 3.2 newtons going up. So the resultant force is going to be 3.2. Take away 2.0, 1.2 newtons, and the direction is of course upwards. The 3.2 newton force wins. And then we know a mass, don't we? So acceleration equals force divided by mass. That, when I say acceleration is force divided by mass, that force is the resultant force divided by 0.2. 1 divided by 0.2 is that 6. Again, same as before, it's a 2 significant figure question. 6 meters per second squared. Okay, then a nice little explain for the ends. Explain how the magnitude of the acceleration changes from it's released until the first time it returns to its resting position. Okay, so at the start, we've stretched it down to here, and then it's going to go up, and the spring is going to become a bit more compressed, and we go to there. So the question is, what's going on? So refer to forces. So the force is acting on this. We've got a weight going down. The weight going down is the same. Don't know how well I've drawn it in those diagrams, but let's probably call it a tension force of the spring is going to be larger in this situation than it is here. In fact, if that here is the rest position, the tension should be equal to the weight. So as after the re-release, after the spring is released, the extension decreases. Okay, as it goes from diagram 1 to diagram 2, and obviously you can make diagrams if you want to in your explanations. So as the extension decreases, the force. So this is the force from the spring. I've called it tension over here. I'll just call it force from the spring. The spring reduces. Okay, so eventually at the rest position, the force on the spring equals weight. So therefore, at this position, there is no resultant force and no acceleration. Now, I've gone quite a bit over the space they've given us here. There's 3 marks. Yeah, have I even answered the question? Yeah, there is no resultant force and no acceleration. I think I'd put at the end, i.e. acceleration reduces to 0. Yeah, okay, I think they were expecting to start with that final point. So acceleration starts high in diagram 1 and goes to 0 in diagram 2. And as the extension's dropping, the force on the spring is dropping, and eventually they're exactly the same. So yeah, it didn't give us much space to do that. I think they were possibly expecting a shorter answer than what I wrote there, but that's how the solution came to me. Okay, South Pole, you need to know that the direction of the field is from north to south, so these field lines are going in this direction. Which of these is attracted to the bar magnet? If placed in the magnetic field, you need to know that the magnetic elements are iron, nickel and cobalt. The strength of magnetic fields changes as the distance from the south. So the important thing here is field lines are closer together in a stronger field. Okay, so as distance increases, the field lines, you can see in the diagram, as you get further away as we go this way, the field lines get further apart. So what this means, as the distance increases, field lines are further apart, so the field is weaker. Okay, piece of iron that gets put into a magnetic field. Iron is a magnetisable material. Is this what the question is about? So a piece of iron becomes magnetised. Explain why the piece of iron experiences a force towards the south pole. In other words, that is the magnetic field that has been induced in that piece of iron. So you may add to diagram 2. So the north pole, I do like to write in bullet points, you'll see me putting those in. The north pole is induced on the side closest to the, I'll call it a permanent south pole, and then north pole is attracted to the south pole. Okay, so opposite poles attract. The student suggests the piece of iron is now a permanent magnet. Okay, now iron is a soft magnetic material. Okay, iron's a soft magnetic material. So what does this mean? It loses its magnetism when removed from the magnetic field. Lovely. Okay, we have a parallel circuit here. Why? It says an advantage, okay, explain an advantage, okay, so just be careful of, thinking, oh, it's 2 marks, do I need to say 2 things? Well, you need to say 2 things about one advantage. So the advantage, I think most likely, a lot of people say, if one of them breaks, the rest of the circuit will still work, but I think given that it's a house, the most important thing is there's switches here, so I think that's what I'd say. Each lamp can be controlled independently. And the reason for that is each lamp is in its own branch. I think I'll tell them that I know it's a parallel circuit as well. So each lamp is in its own branch of the parallel circuit. Okay. Switch 1 is closed, the current is 22 milliamps. The name of the particle is the electron. Show that lamp 1 has got a power of 5 watts. So because it's a series circuit, the voltage across all of these, all of those branches is 230 volts. So power is current times voltage equals, to keep scrolling up, 22 milliamps. Milli is 10 to the minus 3, 1,000 divided by 1,000 times by 230, and that comes to 5.1 watts. A show that question means give me one more significant figure. So they asked me to show that it's 5. I do that by showing that it's 5.1. Calculate the energy transferred to lamp 1 when it's on for 30 seconds. E equals power times time. 5.1 times 30. Obviously look out for these. You'd be able to do this question even if you couldn't do the previous question. You'd sub in 5 instead of 5.1, but I know it's 5.1, so I know that the actual answer is 153 joules. So yeah, I'll probably still round it to 200 to 2 significant figures. The circuit's connected to the mains. State what is meant by voltage. Make sure you know this. Textbook definition. Voltage is the energy transferred per unit charge. Switch 1 and 3 are closed, which turns on lamps 1 and 3. Switch 2 is open. Calculate the current. Okay, so switch 2 is open. So if this one is open, this means that this current doesn't flow, so we don't have that current. So we've got a current of 22 plus 17 milliamps. That's the question really. 22 plus 17 equals 39. Well, we're obviously in milliamps, so it gives us that already. 39 milliamps. Okay. 2 rays of light. What's happening here? So they're incident on a boundary between air and water. Okay. We've got a refractive index. Explain the paths of the 2 rays of light after they strike the boundary between air and water. Include calculations and draw a diagram to support your answer. Crikey, quite a lot to do here for 6 marks. So when you always draw the normal, okay, and when we're going into a denser medium, it's going to bend towards the normal, okay. So I think the kind of interesting angles here are, that's my angle of incidence for A, that's my angle of incidence for B. Angles of incidence were always between the ray and the normal. So that's my angle of refraction for A, and that's my angle of refraction for B. Okay, I think it would be sensible to actually measure these. You do need a protractor for your physics exams. I think this angle is something like 36 degrees, and I think this angle is something like 60 degrees. So measure those with your protractor. Okay, so right, let's maybe start thinking about what we're going to get the marks for. So Ray A, Ben. Oh, am I going to say? Do you know what? I don't know if the word bends is the best word to put in the exam. So Ray A refracts towards the normal. I'll probably say the same about Ray B as well. Ray B refracts towards the normal. Make sure you know what direction it's going. It's going towards the normal. I've measured my angles. Let's work out some, let's show them that I know the equation. Okay, so R is going to be equal to inverse sine of sine I divided by N. Okay, so R for A is going to be inverse sine I is 36 degrees divided by 1.33, and R of B is equal to the inverse sine of sine 60 degrees divided by 1.33. Okay, let me just type these into my calculator. Sine 36 over 1.33. This one comes out to be about 26 degrees. And this one turns out to be about 41 degrees, something like that. I mean, I'll maybe add these to my diagram. 26 degrees, 41 degrees. Quite a lot to do here. I'm not exactly sure what the marks are for, I must say. So I think I might talk about what it does say explain in the question. I haven't really explained yet. So I might say water and air have different refractive indices. Okay, so that's probably the first thing to say. Now, what does that mean? It means light travels slower in water than in air. I feel like I've said a lot of things for this. I don't know if I can add any detail to this. I think I've hit 6 marks there. Okay, pressure question. We have some water in a bottle. You might have noticed this. You seal it in. Pressure outside is 80. Right. State means this. Just tell me the answer. Right. This is an easy question. So the air pressure outside the bottle, we've taken the lid off. We've let the air in. So that air, just before you seal it, or just after you seal it, just as you seal it, has got the same pressure inside as it does outside. So the air pressure inside the bottle is 80,000 pascals. Okay, as we descend, the air pressure changes, and we've now got obviously higher pressure on the outside because we're lower. In fact, this is the question. So the air pressure increases, and I mean the air pressure. Yeah, so the pressure increases. This means there's more force on the outside of the bottle. So what that force is going to press it in, as you can see there. Explain how the gas molecules exert a pressure on the surface of the bottle. So the idea that you have air molecules move in random directions. Okay, so as they do so, they collide with the bottle. force on the bottle. And, you know, pressure, always give an equation if you can. Pressure equals force divided by area. Yeah, you can also draw a diagram if you want. If you want to draw some sort of particles moving in random directions, you know, you can see that some of them are hitting the bottle, some of them aren't. Something like that maybe would help your answer. Question 10 starts with, in fact they tell us the formula, weight equals mass. You need to make sure you've converted that into kilograms, so you're going to divide by 1,000 to put that at 0.25 kilograms. 0.25 times 10, 2.5 newtons. Part B. Okay, what you are doing is you're changing out. The independent variable is what you change, so you are changing the length, and you are measuring measure the height. Okay, you're measuring the height, how far down it bends. Okay, the control variables are going to be everything else basically, so the mass that you're putting onto it, the bit of wood you're using, what could we say about that, the thickness of the wooden strip, something like that. How could you accurately measure height? Let's have a look at the diagram again. Oh, it's a tricky one, isn't it? So yeah, a few things to say. These sorts of questions are often the same. So name a piece of apparatus. You're going to use a meter rule. I'd say, you know, get down to eye level with the apparatus. Get down to eye level with it. You know, you're going to have to ensure you're measuring it vertically. So you could put, you know, basically a pendulum down like that. So we call that a plumb line. Okay, so something like that. Use a plumb line. To ensure ruler is vertical. Loads of stuff you can say for this question. You could also talk about clamping the meter rule in place, something like that. But yeah, I think those are the three things I'd say. Name the apparatus, meter rule, get to eye level, make sure the meter rule is vertical. Okay, this is your results. Use diagram 2 to determine the height in the lab. Oh crikey, 1 centimetre on the diagram is 10 centimetres in the lab. Blimey, okay. I've not got this to scale necessarily, but you're going to measure that distance. I understand that distance is 3.1 centimetres. I see. Okay, so you've got 3.1 centimetres. Sorry, let me just actually not done that very well, because we're measuring to the height that the ruler goes down to, so we're measuring that distance there, which is 3.1 centimetres. Okay, because 1 centimetre in the diagram is 10 centimetres in the lab. That's a factor of 10 that we're going up by. So this is going to need to multiply by 10, equals 31 centimetres. Okay, tricky one, that bit of a weird one. Okay, now we've got to plot the results. So let's just see what we've got. Length needs to go up to 120, height needs to go up to about 80. So this is going to be 20, 40, 60, 80. Yeah, so just clock that normally, because they give you a piece of graph paper, there's normally an obvious scale. Okay, and if you're fighting against the scale, you're probably doing things wrong. So again, this needs to go to 80, 20, 40, 60, 80, yeah. Just, if you're doing something different to this, you're probably misunderstanding the question, what you're expected to plot properly. So I'm going to plot this by me. Okay, so 20 centimetres of length gives us 2 centimetres, 40 gives us 8, 60 gives us 18, it's going to curve, 80 gives us 31, 100, sorry, that one we don't know actually, that's the next question, I do apologise. 100 gives us 53, 120 gives us 71, that's from the results here, is it? Nice. Okay, concludes that H is directly proportional to L, and actually we've got a curve of best fit, don't we? So no, this is not correct. Graph is not a linear so we do know this. Sorry, I was a bit confused about what that missing point was there. We do know 31 because we've got it from the previous question. Yeah, sorry about that, being a bit slow there. The graph is not linear, therefore is not directly proportional. And to be directly proportional, it should go straight through the origin as well, which it does do, hence I'm not mentioning it here, but it needs to be a straight line. Okay, question 11, we've got this, these sort of rechargeable batteries you might have used to charge your phone, and yeah, we've got some weird units. So we're using amp hours, and we need to convert that into coulombs. So 1 amp hour is when a current of 1 amp charges for 1 hour. And that's the same as 1 amp charging by, in standard units, 3,600, that's 60 times 60 seconds. So 1 amp hour, which if you ever look up the specification of mobile phones, is the standard unit they give for capacity of batteries is 3,600 coulombs. An electronic device is connected to a power bank. We're told currents, we're told charge, time equals Q divided by I, 3.8 times 10 to the 3 divided by 2.4. That comes to 1,600 seconds. You'll notice it says give your answer in minutes, so I have to do 1,600 divided by 60. Can't quite do that in my head. 27 minutes to 2 significant figures. Let me just check I've done that right. Yeah, lovely. Very good. Okay, the electronic device is connected to the power bank using a long cable. Suggest how this affects things. Well, a long cable has got more resistance. Okay, much more resistance. This means that the current will be lower. What's this mean? So the time taken will be higher. Very good. Okay, own 3 devices, each with a different amount of charge can be stored. The power bank stores a maximum charge of that. You need to take them away. What is enough to recharge the batteries? Crikey. Okay, there's quite a lot to do here. So, in 1 week, device A needs 2.4, and you need to charge it every day. So device A needs 16.8 amp hours of charge. Device B needs 4.2. Oh, I suppose, but if you need to charge it every day, do you need it that first day? Is it just times 6? I'm not sure. I'll think about that in a second. This needs to be like, as a school trip, you don't need to charge it on the first day because you charged it at home yourself. I'm not sure. Yeah, okay, I'm going to think harder about that one. Let's hope it's not ambiguous. B is that, and C, again, we're going to just charge this once. So it's going to be 6.8 amp hours. So the total, 16.8 plus 4.2 plus 6.8. The total is 27.8 amp hours. Oh, it is a bit ambiguous. Okay. So 27.8 amp hours is larger than 26.8 amp hours. Determine, so cannot fully charge them, or I'm just wondering if that device A, do you only need to charge it 6 days? If it's a school trip, you know, if we're going Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, that's what we're assuming. Monday you don't need to charge it because you've charged it at home, so you've only charged it on 6 days. At which point it would be okay. Yeah, I'm going to just assume that it is 7 days, but I'm not massively happy with that. So what if I said, so 27, this is larger than the capacity, so cannot fully charge them all. I feel like we've made 1 point doing the maths, 1 point comparing it to the numbers, 1 point coming up with the answer. So we've probably got one more thing to say. You know, we'll have to recharge the power bank in order to fully charge the devices. It's a little bit unlucky that 27.8 is so close to the 26.8. For me, if you're going for a week, you actually only need to charge it 6 days, but yeah, there we go, not massively happy with that question, but let's keep moving. Question 12. Okay, we have a velocity time graph. Okay, what's the acceleration of the car at 20 seconds? So the acceleration is the gradient. Now we have a curve, so in order to get the, this would be a bit easier hopefully with a ruler than with my stylus. So, oh crikey, apologies for completely horrendous use of stylus here. We have a rise of 64, and we have a run of 62. So we have a rise over run of 64 divided by 62, just over 1.03, something like that. 1.03 meters per second squared. I wouldn't be surprised if I've done that slightly wrong. Hopefully you've done that with a ruler and it's a bit better than I've done it there. Ooh. Something like that. Determine the distance travelled during the first 80 seconds. Oh blimey, I'm going to have to take this again. Okay, so the first 80 seconds. Are they really expecting me to... Sorry, I'm going to have to actually rub out some of... I'll just rub everything out because this is going to get... Sorry, don't do this in the real exam, just do it with a faint pencil. 80 seconds, how are we going to do this? If I just try and do that, is that roughly the same? Just a little bit less than that. Try and do something like that. Okay, I feel like, so sorry, what am I actually doing? Distance equals area under graph equals area 1 plus area 2, where I'm calling this my area 1, this my area 2, and you'll see that, you know, it's not perfect in terms of the curve, but it's not a bad approximation. So area 1 is 64 multiplied by, what's this distance here? 34 by 64. Times 64, 2,176 metres, and area 2 is a triangle, 64 times 46 times half. Half base times heights. Is 1,472. Add them together. It gives us something like 3.5 kilometres, 3,648. Probably did 2 sig figs, it's a bit loose. 3,006. Sorry, I said kilometres earlier, I meant metres. 3,600 metres. Explain the motion of the car after 80 seconds. Okay, so after 80 seconds, that's when the gradient equals 0. What does that mean? It means constant speed. Explain the motion of the car. Sorry, let me just figure out what's going on. Oh, it accelerates with constant driving force. Okay, so it's the terminal velocity graph, this one, just drawn in a slightly different way. It explains, we're going to have to talk about forces here. So, you know, as it gets faster, the drag increases, and at 80 seconds, the drag is equal to the thrust, the driving force. Okay, so there's no resultant force. F equals ma, so no acceleration. Okay, sorry, I've just actually looked up the answers for these. I've not done this brilliantly, I do apologise. This one here, for full marks, needed to be between 1.05 and 1.15. Okay, so I'd have dropped a mark there, I do apologise. If you're doing that with a pencil and a ruler, hopefully you'd have got better than me. And this one here, I do think this is a bit mean. This one had to be within 3,700 to 3,800, so again, I think I'd have dropped a mark there. Ooh, yeah, tricky that. I thought I'd done okay, but apparently not. I'd have, yeah, dropped